Let's welcome Mridul Agarwal from the Department of Industrial Engineering to present on multi-objective reinforcement learning with nonlinear scalarization.
Hello, share my screen.
Yep, we can see that.
This screen? Thank you. Hey everyone, I am Mridul. I'm presenting my work on multi-objective reinforcement learning with nonlinear scalarization. I performed this work under the guidance of Professor Agarwal. So, we can start now. I'll give a brief introduction of reinforcement learning first. So reinforcement learning essentially tries to, in reinforcement learning, there's an agent which interacts with an environment and observes a state ST and performs an action AT, and then it obtains a reward RT and transitions to a new state. So this is a format of stochastic optimization where I have a sequence of steps and my system dynamics that how I transition to the next state and what reward I observe is possibly unknown. Now, I want to perform an online learning that I want to simultaneously learn the system and I want to obtain as much as reward I can in the simultaneously. So, reinforcement learning has been recently made very popular with AlphaGo, where they beat the current then world champion Lee Sedol, and it has been actively been used in data center cooling, UAV optimization, robotics, and many other applications. So based on this, we ask few research questions. What happens when the obtained reward is vector? In the previous slides, the RT is typically assumed to be a scalar, but what happens when it is a vector? Is it different from standard RL? And if yes, how? And how do we construct algorithms and perform analysis? And how can we make the system, how can we learn the system faster? Is this problem even relevant, first of all? Yes, we see that if we have a, first motivation comes from the wireless scheduling application, where I have a cell phone tower, which tries to allocate resources to two user equipments, one having a stronger channel and one having a weaker channel. Now, if I allocate all the resources to the UE with stronger channel, it will be very efficient. However, it will be unfair to the second user. So I want to have a trade-off between the two users, and that is typically used as proportional fairness, and that is a nonlinear function. Similar problem comes in traffic scheduling, where I have multiple lanes and each of the lane can have different arrival rates, and I want to control the traffic light in a way that it results in the maximum use and while not allowing any detrimental effect on the lane which has slower incoming traffic. So this motivates the problem of multi-objective reinforcement learning and while using nonlinear scalarization. So going forward, we first formulate the problem mathematically. We have a state space S and action space A. We assume that we have Markovian transition dynamics. That is, my next state depends only on the current state and the current action. And I have K reward kernels. Since we assumed a vector reward, now each of the element in the vector is a reward kernel. And the reward vector essentially was the RT capital RT was essentially a K dimension vector. And I have a policy pi, which is a distribution of action over the actions given the current state. And now I define the joint or cumulative rewards for each of the kernel, which is the expected discounted cumulative reward. And this gamma is the discount factor, which is typically less than 1. And what I want to optimize is a concave objective, which is a concave function f of the individual reward kernels. And this function takes in the input as the cumulative reward for each of the reward kernel. And I want to find the policy pi, which maximizes this concave objective. The choice of this concave objective is inspired from economics, where we mostly use concave utilities. So some common examples of this are linear combinations, which are obviously concave, then proportional fairness, which is widely used in wireless scheduling, and alpha concave utilities. So why cannot we use current RL algorithms with just using the function value as my reward? Will that not work? No, actually, in that case, the problem becomes non-Markovian. For that, I would need to have the entire history of my actions, states and rewards to determine the current action. And that becomes really tricky. Further, for a Markovian policy, the optimal policy is not a deterministic one, which is what we could have obtained from Q-learning and SARSA type algorithms. So this is the fundamental problem in this thing. So we know that with scalarization as rewards, my standard Q-learning will not work. My A star is not argmax of QSA, which is true for the scalar rewards. However, as we observed in the last slide, that my optimal policy is not deterministic. So when we learn policies using policy iteration, we can also learn stochastic policies, and they do perform better than the DQN kind of algorithms. However, they're still not optimal. In the prior works, what people have done is they have linearized the function f, and we try to alleviate this linearization by directly considering the nonlinear functions. Another work which is done is they try to perform an action which maximizes the function of the Q values. Now, this performs better than the standard Q learning. However, this action is still this results in a still a deterministic policy, and this is still a suboptimal as we have seen from the previous slides. Lastly, a very recent work considers the different approach. What they do is they push in the expectation over the rewards to outside the function, and what they write is f expected value of f of summation of rewards. Now from the concavity of function, this is suboptimal. So we first propose our solution method. What we consider is we consider a steady state distribution of states and actions. So we write the problem as maximization of steady state or steady state distributions. We have a concave function f, and we write it as a function of summation of rewards and the distribution in which and the probability of being in state and action, state S, and taking action A. Now, this is a convex problem because my function f was concave. And I have some constraints because D has to be a valid distribution. It is non-negative, and the sum of all the S and A's so should be 1. So an inherent assumption in this is that my state and actions are finite. And then my D has to be a steady state distribution of the Markov chain induced over the states. Now I can use this to obtain my optimal policy as a conditional distribution of action given the state. Now, how do I construct a learning algorithm from this? I know that given a transition kernel, I can obtain a policy, but how do I learn this? So in literature, there's an optimism in the face of uncertainty approach, which searches for the best possible Markov decision process and finds the policy for this. However, this is computationally very complex because now I have a complex function to optimize. So what we propose is to use a posterior sampling of transient probabilities, which is another common approach in literature, where they don't try to find the best possible MDP, but sample from the set of possible MDPs. And for this, we use a Dirichlet distribution to sample the transition probabilities. So we obtain certain theoretical results. So we first note that when f is a monotone increasing function, the optimal policy is Pareto optimal. That is, no other policy can obtain a higher reward without that causing a decrease in the joint reward in the reward of another objective. Further, when my f is L Lipschitz, my convergence rate of the posterior sampling algorithm drops as SA DLK by root T. Now this is optimal in terms of T. That is, if I play my algorithm for T time steps, then my convergence to the optimal policy reduces as root T. Now, in the previous slide, I said that my state and actions are finite. However, what if they are not? So we next propose a solution for model-free approach. Here, I do not directly learn the transition kernel, but I directly optimize for the policy. So we first propose a gradient ascent-based method, which is a use of chain rule. From here, we obtain the gradient on the function f and learn a policy pi. Now this policy pi can also be parameterized and be trained in a similar function as we train in standard RL algorithms. However, the gradient term is very different, and this is where the magic happens. Further, this is also extendable to actor critic methods by using the Q for individual objective K. And this idea is essentially similar to the earlier Q learning method with scalarization as reward. So we also perform the simulations empirically. And we first consider the problem of fair slot allocation to users. You have a finite state space for every user. Every user can be in a good state or a bad state, and based on that, they can get a reward which can be high or low. And we consider 8 users. So we compare it against the RA versus XI policy, which is known as the standard, which currently works in standard and is shown to be optimal. We see that the model-based algorithm can achieve the performance of the upper limit, and model-free algorithm is reasonably close to the upper limit. However, the vanilla policy gradient, which uses the reward as scalarizations, is not even close to the true optimal policy. We also see how the convergence works. In the second step, we go to a continuous state space and we use the alpha concave utility. Here again, we consider 8 users, and now we see that the policy gradient algorithm is able to converge to a better policy and is able to obtain higher scalarization values. However, the vanilla policy gradient, which uses the rewards as scalarizations, is not even able to learn anything. Lastly, we also consider a queuing system where we have 8 heterogeneous queues that the arrival rate of each queue is different, and the server time needs to balance the server to each of the queue. Here again, the model-based the multi-objective policy performs better than the round robin or uniformly random schemes. Here are some associated papers with this area, which we wrote in the last 2 years. Now, we ask for the third question, which we ask is, how can we extend this work when we have multiple agents trying to solve a similar problem, and how do they collaborate to get a faster convergence to the optimal policy? For this, we have M-parallel agents, which are trying to optimize against an identical environment, and they try to collaborate to learn the system faster. Here, we provide the first formal analysis on RL, which uses concentration inequalities for M independent martingales. Now, however, if we share the knowledge, then we run into the problem of large number of communication rounds. So how do we reduce that? For a total number of total interactions, we are sure that we can only need to communicate order of log t number of rounds, as we can still obtain the order optimal regret. Thank you. So this work was not done with the help of other professors and other students, and I would like to acknowledge them. And thank you. Do you have any questions?